Welcome, everyone. Is this thing on? Hello? Perfect. I'm really happy to see so many JavaScript developers in here excited about the new Async and Wait. Someone's leaving. I'm kidding. This is C#. I promise. Someone actually left, so I really hope they're coming back. All right, so we're going to be talking about efficient Async and Wait and how to kind of use the best practices when you're building C# applications. Efficiency can mean quite a lot of things. It can mean that we want to build applications that perform really fast or really good for our end users. It can mean that we are efficient in terms of building code faster and making sure that we follow the best practices to ensure that the applications aren't crashing on us. We are going to cover a few of these different things in this talk, and hopefully by the end of this you'll have some goodies that you can bring back to your applications and make sure that you're using Async and Wait properly in your apps. My name is Filip Ekberg. I've done a few talks on C#. I have a book on C#. I have a course on Pluralsight. So check that out if you like any of my stuff. And you can ping me on Twitter if you have any questions. Or just shout out. I still have a little bit of a bad hearing, so if I can't hear you, it's not that I'm ignoring you. Just ping me on Twitter if I can't get to your question now. So I guess the question is, why would we bother at all introducing asynchronous principles in an application? Really, it boils down to the fact that we want to avoid this type of behavior. We have an application, this is an Android application, and I'm not specifically saying that all Android apps are unreliable, but in this case, I built an application for NDC London that when you clicked a button, the application felt like it was crashing, or the OS told me that this application is no longer responding. So the idea is that we want to bring in asynchronous principles to ensure that we can avoid these types of unreliable scenarios. So one of the efficient approaches is to improve the user experience. I want the application to feel as efficient as possible for my end users. Just because the operating system is telling me that something might be taking a little bit too long of a time, that doesn't necessarily mean that the application isn't doing some heavy work. It just means that we're doing the work on the wrong place. And also when it comes to mobile applications, we need to keep in mind that we shouldn't overuse asynchronous programming or parallel programming, because every operation on a mobile application requires battery and CPU power. So that's something we should keep in the back of our heads. If you go over to the PC world, or Mac world for that matter, we want to make sure that we can use all the resources that we have available. This is my workstation at home, which is pretty powerful. I have a lot of CPU, I have a lot of RAM and a pretty good fast internet speed and good hard drive. So I want to be able to leverage all those different types of resources. And that boils down to two different types of paradigms. We can talk about CPU-bound and IO-bound operations. In .NET, these are approached the same way, but they are fundamentally different. CPU-bound operations, that's parallel programming, where you want to divide a problem into really small pieces and solve them independently, where they have really nothing in common. IO-bound operations could be loading a really large file into memory, which you then later process in parallel. So you can combine these two paradigms as well, which is where it becomes a little bit confusing, but with the help of .NET and something called the task parallel library, we can make this work a little bit easier. And we're going to be looking at quite a few examples of that as well. So in this example here, I'm just loading some really large chunk of data, which I then can process in parallel. But it really boils down to one simple notion of what I want to do. I want to go from something that blocks my user interface or blocks my application. It doesn't make a lot of sense to maybe introduce Async and Wait in a console application. It makes more sense to do this in applications that have a user interface. So I want to take my application from feeling like it's blocking my user from input to something that feels a little bit better. I can allow my users to do more things at the same time. And the way that I do that is by move all the work that I'm doing on the UI thread. I want to avoid doing heavy lifting on the UI thread or the main thread of the application. In the past, this has been rather difficult to do in a good way because you used threadings manually, but now we have APIs in .NET to do this a little bit easier. And one thing I want you to keep in mind is that you should never block an asynchronous operation. So once you've said that, I want to run this somewhere else, never force that to give you a result. There are proper ways to ask for if there's a result available, but you never force it to give you some data unless you know it's completed. Might sound a little bit obvious, but we're going to look at a few examples of that as well, where we crash an application because we're using it improperly. So really, if I look back at that nice Android application. Really what I want to do is I want to take this blocking UI where the OS is telling me that something's crashing, and I want to prompt the user with another type of blocking to tell them that, well, you should wait for a little bit longer. Psychologically, this means that the user knows that the application is still doing something. I'm providing them feedback that the application isn't crashing. Although we all know that if we see this please wait dialog for too long, we're going to end up killing the application anyways, because we don't really want to wait. So there are other ways to approach this as well, but this is just one of the ideas behind why we want to make our user interfaces a little bit better. And to do this, we want to introduce the task parallel library. This was added in .NET 4.5, and the whole idea is to simplify working with concurrent and asynchronous code. It's kind of the definition of the task parallel library. So they group these two different paradigms together, where we have concurrent code, which is parallel programming, where we solve small pieces of problems in smaller pieces, and do that as fast as possible using every available resource. And then we have asynchronous programming, which is a little bit different. It's also about offloading work to a different thread or a different something else that's not blocking my user interface. But then when there's a result available or when that operation is completed, I want to be notified. Think of a callback. I want to be notified when there's some data that I can process. And to introduce this in a C# application or any .NET application is really simple. It all starts with task.run. This does a lot of things behind the scenes where it tries to figure out where to put your work. It schedules your work to run on a different thread. It may reuse threads if there's one that's available, so it doesn't have to do unnecessary allocations. So there's a lot of things that's happening here that we probably should keep in mind as well. The idea is that the work is distributed somewhere else to different threads, so it doesn't block our current context. Context is a thread as well. They're kind of used interchangeably. Then one of the interesting things with this task parallel library is that threads on the thread pool can be reused for different tasks. Now, normally when you do thread.start or new thread, that actually gives you a new thread that it's not reused. There's no data available in that particular context. But with tasks, you may have data that's coming from another asynchronous operation that you've done before, because it's reusing data. So there might be thread static data that's still available on a new task, and that can be a little bit confusing. So with that given, you shouldn't use thread static data at all when you do async and wait or task parallel library. And what it also allows you to do, when you do task.run, it actually gives you something called a task back, and you can use this to figure out if there's a result available. You can subscribe to when it's completed. This is known as introducing something called a continuation. So once I've started my asynchronous operation, that could be loading a file from disk or querying a database or something like that. When that's completed, I can go back to that place where I was before, and I can continue doing my work, all without blocking my user from doing additional things in my application. And of course, this here also allows us to return data. As I mentioned, it wouldn't be so useful if we were only able to offload work somewhere else and not being able to ask for data back. Now, the task here is, in fact, generic, but you don't have to explicitly determine which return type it has. That's, in fact, inferred by the compiler. So let's jump out of PowerPoint for a moment and jump into Visual Studio. And I have this application. If I run this, this is a WPF application just for simplicity. It could be any type of UI application, really. Just an easy way to illustrate why asynchronous programming is important. When I click Run here, this application locks up. And if this were locking up for a little bit longer, Windows would have told me that this application is no longer responding. But I don't know that. I don't know that it's not doing a lot of work. So let's have a look at what this code is actually doing. You don't have to know much about WPF to understand this. But basically, we have a click event handler that's calling a method called doSomething. So far, so good. And then we have this method here called doSomething, which is simply updating the UI with some information. And then we have a thread.sleep for 2 seconds. Normally, we only add thread.sleep when we want to solve random problems. Actually, we shouldn't do that, but sometimes it does solve interesting race conditions. But let's just say that this simulates a little bit of work. It could be loading something from a web API or loading something from a store that's a cold storage, for instance. What I want to do now is I want to say, I want to run this work somewhere else. I have two different ways to do this. Either I run this entire method in a task, like this here. I could say task.run, and task.run takes an action, which is just a delegate. So I could pass a reference to that method to say, run this method somewhere else. I don't care. Just run this, and hopefully now my application is a lot better. But if I run the application now without the debugger attached, I can move my window around. It didn't lock up, but also the UI didn't update after those 2 seconds. So now I've introduced a bug in the application. And even though the application feels more efficient, it's a lot more faster, the user will think it's awesome because it's no longer crashing on them, but it's not working as expected. The problem is I'm trying to update the UI from a different thread. Now this is where it becomes a little bit tricky because now I have to communicate back to the UI that I need to update the UI from a totally different thread. And to do that, I can ask for the context that owns the UI thread to invoke work on that. Let me just show you what this looks like, and you'll understand why this is a little bit, I don't want to use the word nasty, but it doesn't look very pretty. So I can say that I need to invoke some work on the UI thread. This is very WPF specific. Each UI framework has its own way of doing this. But basically, you have to then invoke the UI when that's done. A better approach would probably have been to move those 2 seconds worth of work to a separate thread. Instead of moving this entire method and wrapping this synchronous call, I would say, in a whole task.run, a much better approach would be to undo this and look at this in a little bit of a different manner. This is one of the things you should avoid doing. You shouldn't just simply wrap your synchronous operations in new tasks. You should go to the root of the problem. And the problem here isn't the call to do something. It's, in fact, what it's doing internally. So we have to drill down here and figure out how do we move this to a different thread, right? Something like this here. So now what happens here is that if I run this, the application is going to behave a lot better, but it didn't take 2 seconds before I got the result from Filip, because actually what we're doing now is that I'm saying, run the method do something, update the UI, then run some work on a different thread, then immediately run this line of code here at the bottom. Right? So it just offloaded those 2 seconds worth of work, but what if this thing here at the bottom relies on the result of this operation? Now this here introduces an asynchronous operation, which means that I can subscribe to when this is done. I can say that I want to get the result of this. Let's say task. And I could say that I want to continue result task. I could say that after this work is done, I want to continue doing some other work, like this here. So now what happens is that after 2 seconds have been operated on a different thread, I want to go ahead and update the UI. And if I run this without a debugger, we're going to get hello from NDC or hello NDC, but the second line never shows up. This is because with the task parallel library, all the continuations are executed on a different thread as well. It could be that it's executed in line with this thread here or this task. It really depends on how you configure that. And the runtime is pretty smart enough to try and do some really smart optimization for you. So again, if I want to update the UI from this place, I'd have to introduce the dispatcher. And now we've made the code a little bit, we've made the code unreadable, but at least we've introduced asynchronous programming. So now, hopefully after 2 seconds, this is now going to update the UI. So I've solved one problem, but even though the application feels a little bit more efficient, this code here is not going to be very efficient to work with. It's very, very fragile. It's very easy for me to make the mistake of not introducing this cross-threading to talk back to the UI thread. There has to be a way for us to work with this in a better approach. And of course there is. We're going to look at Async and Wait, which hopefully solves all our problems. But first we have to understand exactly what happens here. One thing that you didn't notice, because I didn't run this with the debugger attached, if I take this line of code here and run this without the dispatcher, and I'm going to run this with the debugger, because that's going to capture all the exceptions that happens when I debug the application. I'm going to click on run here, and hopefully, after 2 seconds, it's going to tell us that we in fact had an exception. So there was an exception thrown inside this continuation because it couldn't update the UI from a thread that wasn't owned by the UI. Trying to do cross-threading without that dispatcher nastiness that I had to add for WPF. But how come the application didn't crash here? It's because tasks in general, they will capture all your exceptions, or they will swallow your exceptions. So if there's an exception, even if I have an exception inside, if this operation, if I replace this with a throw new exception, that would in fact just not do anything. The application wouldn't crash because that exception would live on this instance of the task here. So how do we check if there's an exception? Well, you'd have to do that inside one of these continuations. So you could say if result task is faulted, and you can then grab the exception to check that. All right, so that's not too bad. But how do I know if this continuation failed? Well, this also returns a task, so you'd have to say this task.continue with, this takes the task, and then you'd have to check if this is faulted. Get the idea, right? T is faulted, and so forth. And then to check if that is faulted, you'd have to add another continuation, and so forth. It doesn't get very pretty, right? So this is all the way back in .NET 4.5 and prior to adding Async and Await. But it's important to understand how all of this works because Async and Await uses this internally, quite heavily actually. It's built on this. So if you don't understand the fundamentals of the tasks, it may become really hard to efficiently add Async and Await in your applications and use that in the best approach. All right, so there's one more thing I want to show you here actually, before we go ahead and talk about Async and Await. Let's say that we'll get rid of a little bit of code here. Here we go. Let's say that instead of having the text from Filip said here, let's say that we return this from this task up here. After those 2 seconds, I want to return that from this asynchronous operation. Now, to access this result, I have to do that inside the continuation. Inside the continuation is the only place you're ever allowed to do your task.result because you know you have a result here. Calling this property is in fact a blocking operation, so if there's not a result available, it will block the entire thread until that's available. That means if we were to do that like this here, our result is equal to task.result, looks the same, but it's really not. What this does here is that this is going to block the UI thread. The current thread is going to be locked until that result is available, unless it already completed. All right, so, and this here is now going to be turned into a task of tResult or a task of string. All right, so with a little bit of an understanding of the tasks and how you add that, there are a few considerations that you should keep in mind. You should be careful when you wrap code inside your tasks or using task.run because that can be a little bit problematic. As we just saw here, it might seem like the application runs really quickly, but we introduced a few bugs. And unless we capture all those exceptions or have the debugger attached, we won't know. And I didn't show this, but thread static data is unreliable. You can use something called async local if you really have to have static data inside your tasks. But if you do need to do that, I would recommend you read up on async local. And then another consideration with tasks is that we should always validate the tasks. And that means that we should always check that if there was an exception or not. And with the task parallel library, that becomes a little bit tedious because you have to add continuation after continuation after continuation, and that doesn't look very pretty. So hopefully we can solve this a little bit better with async and await. Before we get into async and await, I just want to show you this little portion of code as well. Parallel.for it's also part of the task parallel library, but that's a blocking call, which means that to solve your problem in parallel, this here is going to run from 0 to 100, or it's 0 to 99. And that's actually going to use your current thread as well to solve the same problem. So if you want to offload that to somewhere else to not block the UI thread, you always have to wrap your parallel for loops or parallel for each loops in a separate task. All right, so let's talk about async and await. These two keywords were introduced quite a while ago, but it's still one of those things that people tend to get a little bit wrong. And it's really easy to get it wrong as well because the designers of this feature made it really easy to add it anywhere without a lot of implications. So these are just contextual keywords, which means that they do a lot of compiler magic to solve the same problems that we could do without async and await, but they do add a lot of code behind the scenes, and we should understand exactly what that is. So when we add async and await, the idea is that all the complexity that we just saw with the continuation and all of that, it's going to hide that somewhere else. Hiding complexity is always a good idea because the code becomes much easier to work with, but it's also a little bit more fragile. So it promotes readability. It makes the code easier to read. You no longer have this nested calls or this looks like an arrow in your application, but instead it looks very fluent and you read it from top to bottom and you quite understand exactly what's going to happen. But one issue is that it's a little bit more error prone. And that's because it hides the complexity in something called a state machine. So how do we add this to an application? Well, it all starts with the async keyword. This is very simple. Method here returns a task. We can see that it doesn't actually return a task anywhere because the compiler takes care of that for us. So adding the async keyword does a lot of magic behind the scenes. But I guess the question is, does this make the code asynchronous? Can we use this all alone without doing anything else? And the answer to that is no. The async keyword alone doesn't do anything in particular other than introducing a lot of complexity, and it moves your entire method body into a generated class. But it doesn't run anything on a separate thread. That's all done by this task.delay here. So when I introduce task.delay, that's doing some work somewhere else. It could be an HTTP call, it could be a web loading something from disk. So this way to simulate some work. And you use that together with the await keyword. So these two keywords should always be used together. The reason you're allowed to use async alone is for I guess, virtual methods and all of that, and where you don't have the method body at place. I don't know. They've just introduced that. I believe they should have made it so that you have to always use them together. Anyways, there's a lot of things happening in here. First thing moves this method body to a different class. The await keyword is now in charge of making sure that the code at the bottom is executed only when that asynchronous operation is completed. So the await keyword is now what marks for something known as the continuation. You know that continue with method call that we had earlier. We no longer have the method call, but it's still the same concept. Internally, it's going to use that continue with method to run the code after the await keyword. Sort of. It has a lot of more code than that, but basically it does that. It's also making sure that it validates the success or failure of the task. So we no longer have to check if it's faulted on our own. This will, in fact, validate the entire chain. So you no longer have to do continue with and check the default state and all of that nastiness that we had to do earlier. What it also does, when it reaches the await keyword, it returns to whoever called the method. And this is where it becomes a little bit tricky to understand. Because what happens, I'll go back here just to show you this portion of the code here. When it reaches the await keyword, it returns to whoever called run async. Right? Because it can't run the final code because that's inside the continuation. So whoever called run async will then be able to execute the next lines. All right, so always use them together. That's really, really important. So let's have a look at how we can make our code a little bit better. Here we go. So instead of having all of this code here, let's now introduce async and await and see how this is going to behave a little bit different. I really don't like this whole idea of having to use continue with, but instead, I still have to move the work to a different thread by doing task.run, right? But I don't like this. So instead what I want to do, I'd like to await the task, and then I'd like to update the UI. We no longer have the result task, so that would be task.result instead. But as I mentioned earlier, we should avoid using .result. We could use .result here because I know that it's been properly, we've awaited the task, which means that what happens here is that it's not going to run that portion of the code before it actually has a result available. But the best practice is not to do it like that. So what can we do instead to get the result out of the task? So the await keyword, it validates that we have not a faulted task, there's no exceptions. But it also gives us the result. And then I can use this here at the bottom. And we can see here that this here is a string. So what await does is that it makes sure that there's no exceptions, and then it grabs any results out of that task. So it would get the text from Filip. And I already had the async keyword here at the top, which I shouldn't have had. But as you'll see here, I get a little bit of a squiggly here telling me that you can't use the await keyword. You cannot use the await operator or keyword without the async keyword, but you can have a method call with the async keyword without using an await. So now, if I just add the async keyword here, and I'll run the application, and we'll just make sure that it still works the same as before. I can run this here, I can move the window around, and after 2 seconds, it says, hello, NDC from Filip. So now that I've added this here, I said earlier that when it reaches this await keyword, it in fact goes back to whoever calls this method. So if we look at where this is called from a click event handler. It calls do something. That means that when it reaches that await keyword, we should be back at this line here. So if I do debug.text plus is equal to test, or waiting maybe better. Let's do that. And I'll run this here. Hopefully it's going to say hello NDC and then test ... and then after that it's going to update with the rest of the text. So what actually happened here is that it was stepped through this. It's going to call do something. That updates the UI. That offloads some work to somewhere else using the task parallel library. And then it sees the await keyword. Now what this does is that it validates that there was no exceptions. So if there's an exception in here, throw new exception, like this here, this will be thrown back to whoever calls this method, and they can handle that. Or in fact, it will be thrown back to whoever uses the await keyword. So when we have the await here, we have the option of wrapping this in a try-catch block to make sure that we can catch any potential exceptions, right? And then after that, when it sees the await keyword, it returns back to run this code here, and then the user can update the UI and click around and do whatever they want. Then after 2 seconds, it runs this code here. So what happens now if I run this here? Obviously, I have a throw new exception. The application is going to crash. That's no good. So I want to handle this. But if I don't know what happens inside this method, I just know that this is an asynchronous method. What happens if I wrap this in a try and catch block? I'll run this without a debugger. Hopefully now this application works as it should, and I click run here and the application works, but it doesn't. For some reason, the application still crashes. If I run it with the debugger attached, and I'll put a breakpoint in this catch block here, click run, we can see that I did get the exception. And it's validated by this await keyword here that inside the task there was an exception. We caught that, and it's now going to be thrown back to whoever calls this method. But then suddenly I'm somewhere else, and the application didn't actually catch this. So the problem here is that I would need to validate that this method also worked properly. Does that mean I can just add, since it's an async method, could I just add the await keyword in front of that? Let's try that and see what happens. If I do await, it's going to tell me that this method is not marked as async, so I have to do that first. But there's still a little bit of an issue here, because we cannot await a method that's void. It doesn't return anything. So how would it await that? How would it know that this is an asynchronous operation? So for the consumer of the method do something, this here doesn't in fact do anything more than just run some code that doesn't return anything. So in order for me to be able to track this work and to capture any potential exceptions, it also needs to return a task. This is why you should never do async void, because async void doesn't allow you to track when work is completed. It doesn't allow you to know when data has been available or when the operations are completed. But fortunately for us, there's an easy way to fix this. I can change this to async task, and I don't have to do anything else. The compiler takes care of all of that for us. So what happened now, there's actually a few things that's going on here. Not only did it change what this method returns, it automatically returned a task from this here. But since this returns a task, it also means that any exceptions that happens inside this method is now going to be put on the task that this returns. And that can be a little bit confusing as well. So if I didn't have this await keyword here, I wouldn't be able to capture any exceptions. And you'll see that if I run this with the debugger attached, I click run here, we can see that since I have the debugger, it knows that I have an exception. But then it didn't enter this catch block here, because if I don't await this, it doesn't validate that there was no exceptions. So let's add await back here. And now hopefully the application behaves a little bit better. I get the exception, and I'm inside my catch block. So this here just shows you that it's not as simple as just adding the async and await keyword as soon as you have a task, or it's not as easy as just adding task.run whenever you want to run something somewhere else. There's quite a lot of things that you need to keep in mind. Adding these keywords may seem very easy at just as a first glance, but they do quite a lot behind the scenes. And that's kind of the next part I want to talk about. So understanding just the async and await keywords in the task parallel library, that's great, but you also really need to understand what happens when you add the keywords, what's generated by these keywords to fully appreciate what they're doing. And what's happening when you add the async keyword, it introduces something called a state machine. The state machine keeps track of all the asynchronous code that's being executed and all the work that's happening on different threads. Now, the state machine it's really just a piece of code that's asking, are we there yet? It checks if you have any asynchronous operations that are running. It keeps track of which continuation to run next. And it's pretty clever. What it's doing is that it has this really big code that says, run this asynchronous operation. When that's done, do this, do this, do this. And then it adds itself onto the continuation of the next running task. So it always runs itself whenever the next asynchronous operation is completed. And what it's also doing is that it handles all the potential results and the exceptions. So as you saw here, I was able to capture the exception when I added the task as a return type, but it also crashed my entire application when it found an exception and I used the await keyword. This is because the state machine just handles all of those different cases for us. And it's going to be smart enough to be able to handle some really smart context switches and make sure that sometimes it runs codes inline because that's faster. So even though it generates a bunch of code, it's going to do its best to do that as efficiently as possible. And obviously, a state machine makes sure that it executes all the code after the await keyword. The whole idea of adding the await keyword is so that we can run code when an asynchronous operation is done. And this whole thing that's generated helps us do that. So when we add this async keyword, it generates this entire state machine. That really means that it moves the entire method body into somewhere else. And it's really good to understand that there's a lot of code involved in doing this. So even though I have a really simple method here with very little code, when I compile this and it has the async keyword at the top here, this doesn't no longer look anything like, when this is compiled, it no longer looks anything like what I had earlier. There's no async keyword because the async keyword doesn't exist inside the CLR. The runtime doesn't know anything about async and await. So it has to use async and await internally, or the concept of a task parallel library internally and threading. So it generates a state machine, it does a lot of things with that, it starts it, and then you see here at the bottom, it returns a reference to the state machine's task. So whoever calls the method run async can now keep track of exactly what's happening. Which asynchronous operation is running? Are there any exceptions? Are there any results available? And if we drill into this state machine here and just look at exactly what's happening here, we can see that there's some, if we just go back here, there's var x is equal to 10, there's a task.delay, and then debug.writeLine. So let's see if we can find that inside this portion of the code here. Here's the x is equal to 10, task.delay, and then at the bottom here we have the debug.writeLine. So this here is inside the state machine, and this is kind of a, I wouldn't say a loop, because it's really not. It adds itself onto the continuation of the next running task. So it runs this portion of the code for every time it completes. And it uses the wonderful keyword goto to make this work. I haven't used that one myself in a very long time, but it's used very cleverly inside the state machine here. So we have the task.delay. It checks if it's completed. If it's not, it just returns. So it can run some code after this here. Because in fact, what happens here is that all of this code is executed on, I'll show you here. If we go into Visual Studio, all of the code here, the fact that debug.text plus is equal to hello NDC worked is because this code here is still executed on the calling thread. It's executed on the UI thread. So if this call originates from the click event handler, like we have here, I'm calling do something, there's nothing here that offloads any work to a different thread until we have the task.run. Then after task.run, we're back at the UI thread. It sees this await keyword, and then it adds this to its continuation. So it makes sure that it can do all of this context switching, but it's also important to know and understand that all the coding here is executed on the thread that calls it. So if I were to have a thread.sleep here, this would still block the UI thread, even though I have the async keyword, and even though the code was moved into a generated state machine. There's nothing here that just magically makes this faster and runs somewhere else. Right? I think it's worth mentioning that we shouldn't use async void. It's worth emphasizing that you should avoid that as much as you can. And as we see here, the problem is that we have no way of tracking that this work is done. As you see here at the bottom, it doesn't return any reference at all. So when that method is compiled, we have no way of tracking the state machine and its work or getting those exceptions. There's no way around or recovering from potential exceptions. And that's not very efficient. That means that I wouldn't want to drive a car that was built on .NET where they use async void. Let's just leave it at that. So it's an easy fix, really. We just change a little slight change here. Look here at the top here. Instead of having async void, we have async task. And even though this here is a very, very slight change, it kind of has a big impact as well. Because now we are asking whoever consumes this method to also validate that it completed successfully. And we saw an example of this just a moment ago. So let's talk about deadlocks, which is also one of the things that people tend to run into, or not being able to run out of, rather. What happens with deadlocks is that you end up in a situation where there's no way to recover from, you have one thread waiting for another, and that sounds like a very distant problem, but when you do multi-threaded or asynchronous programming, it's really just one method call away. First, I'm going to show you a pretty bad example, or not a bad example, but one that looks very complex, but the theory behind this isn't that it's too complex. Let's just imagine that we have some work that's happening somewhere else. This could be loading a file from disk or something like that. When that work is done, I want to continue with some work, and I want to do that on the UI thread. Now, that sounds all good, because we saw that this dispatcher that is using WPF to communicate back with the UI thread works really well. But then, at the bottom here, I also say that I want to block until all of this is done. So until this entire operation is done, because I'm adding the wait here after this continue with, that means that this continuation or this task needs to complete before I do anything else. If I block the UI thread, how would this be able to complete? Because it cannot communicate back to the UI thread. So therefore, we have a crash. Now, this seems like it's very complex, and you wouldn't write code like this. Who would ever write deadlocking code like this here? Well, there's an easier way to achieve the same idea, and that's simply to call .wait, or the method wait, or result on an asynchronous method. So how come this crashes the application? I hinted this just a moment ago. Let's go into Visual Studio, and I'll show you. Let's change this method back to method body doesn't matter, unless I still have a throw exception. I'll have to get rid of that. So if I change this back to async void, async task, instead of doing a wait here, if I want to wait for this work to be done, let's do this, just to make it super obvious. Do something and wait. So it looks like I want to take an asynchronous operation and I want to make it synchronous. In some cases, you might have an application that you really don't want anything to be running asynchronously. You want to wait for that result. You have no way of introducing async and await all the way in your application. So therefore, you have to use wait. The problem here is that this here is going to block the UI thread. And I said earlier that all the code inside do something, this here is executed on the UI thread. So if I block the UI thread, how would it be able to do all of this work? How would this task ever be able to complete if it cannot update the UI? So obviously, if I run this with a debugger, a word of warning, if you run this without a debugger, you have to find the process and kill it yourself. So look at that, the application totally crashed. And when it comes to deadlocks, Windows never seems to understand that it crashed, because it's just waiting forever. Right, so I have to kill the application. It makes sense. Now that we know that the async keyword just moves things into a state machine and the state machine is still executed on the UI thread, blocking the state machine from executing means I have no way of waiting for that work to be done. So if I really want to do this, obviously there's always a way to do things you want. So I can say task. I can say task.run. Let's run do something. So this here, let's run this and see if it actually works before I say that it does. I click run here. There was an exception somewhere in this. Did I throw an exception? Yes. All right. The reason there's an exception is because I tried to update the UI from somewhere else. Let's run it without a debugger. So what happened here? The application crashes, and that's good. Because what I did here was that I moved the entire state machine to a different thread. So now what I did here is that I said run do something somewhere else. Block the UI until that work on the other thread is completed. So it runs the state machine, it keeps track of all the asynchronous operations on a completely different thread, and then I'm blocking the UI until that is done. But then, this method here internally has a lot of UI interactions, and that won't be possible because it's from a different thread, right? So that's why you'll end up, you'll end up getting an exception. So you'd have to handle that accordingly as well. So if you really want to block an asynchronous operation, you have to first wrap that in a separate task. But if it has UI interactions, that will fail. And if you try to marshal those calls, or if you have to introduce the dispatcher inside this do something method, you'll end up with another deadlock. So be very careful. And the same goes for calling the result property on a task. If it's not already completed, that would also result in a deadlock. So how do we avoid deadlocks? Well, obviously, we should never use wait or result. We can use wait or result if we know that we are inside the continuation, but only after the await keyword or inside a continue with method. And you shouldn't confuse, there's two methods, very similar named. You have task.waitAll and task.whenAll. Don't confuse these two methods. It might seem like you want to wait to run the next line of code, but that's not really what you want. You want to continue with the next line of code. So there's a little bit of a different wording that you'd use. And another thing to have in mind is you shouldn't share locks. If you have locks in the application or lock objects, you shouldn't share them between different asynchronous contexts. That will also ensure that you have a deadlock. All right, so there's one more thing I want to talk about in terms of the state machine, and that's we want to avoid introducing unnecessary code, because I mentioned at the start of this talk, I said that especially on Android or iOS or mobile devices, you want to avoid having too much code that has to be executed, because each line of code requires CPU power, CPU power requires battery, and people hate you for building applications that drain battery. So we want to build efficient applications. And that sometimes means we shouldn't use async and await, because we don't always have to. So in this example here, I have a method called runAsync. It awaits some internal method, which is also marked as async, which is then also awaiting something, which is then also awaiting something, which is then also awaiting something. This isn't too uncommon, that you have a long method call inside a really big enterprise application where this happens. It's not too uncommon. And someone once said you should use async and await all the way. Sorry, you should use async and await all the way. You should do asynchronous asynchronous principle should be used all the way through the chain of your method calls. But that doesn't necessarily mean adding async and await everywhere. It just means that you shouldn't block anywhere inside that chain. You shouldn't use result or wait or anything like that. The basic idea here is that if you don't need to do anything inside the continuation, you don't need to use async and await. Let me show you why. So I have an application here, which is doing exactly this. It's pretty much the similar application. It has an asynchronous method, which calls an internal asynchronous method, which then calls something else. There's a lot of async and await all the way through this entire application. Now, if I compile this and have a look at the generated code, we can see here that this, in fact, generates a couple of different state machines. And this is a lot of code that's generated for a very simple application or a very simple concept. And if we look at the actual code that was generated, there's a lot of code in here that do we really need all of this code generated or running for each of those different methods? So for every method you mark as async, you're going to get one of these classes generated that holds a state machine, right? And for IoT devices and for mobile phones, that's a little bit unnecessary. So how do we approach this? How do we solve this? How can we improve this application to make the chain of method calls a little bit more efficient? Well, we can still adhere to the same contract. As I mentioned earlier, we can just add the async keyword and that just automatically returns a task. That goes the other way around as well. If I have a task that returned from a method, couldn't I just remove the async keyword and instead return this? And I still have the same contract. I haven't broken anything in the application. And all of a sudden, I reduced one class that's been generated. And if I do this for all of these different methods, let's take the bottom one first. So I want to remove async from this here, but there's also a little bit more of an efficient way of doing this here. What happens here is that I have two calls to two different, let's say, websites. Take 500 milliseconds each. Wouldn't it be better to execute both of these at the same time? Because it doesn't look like they are actually related, so they don't rely on each other. To do that, we can use something called task.whenAll. and I can simply pass an array of tasks that I want to execute, and it will run all of them at the same time and tell you when all of them are done. So I could just return this. So this here is now a reference to two asynchronous operations, and when both of them are done, the task that this returns will be marked as completed. All right, so that's one more state machine that's removed, and we can do the same for all of them. Just remove the async and await keywords, right? And it will all work. And we could even, I believe we could do the same here, right? So we have a continuation. I can probably just return that task because it really references, both of those operations. Right, so I just replaced the async and await keyword by removing the async and replacing the await with a return. And this doesn't work for all different cases. Sometimes you have to use the async and await keyword when you're doing, for instance, an HTTP call. You can't just return the getAsync task. That wouldn't work. You have to await that. Same goes for database operations. You have to complete them and await them inside the method where you called it. But now, when I refresh this application, or compile this and look at this here, there's no longer a lot of generated code. Instead, it's just a method bodies that performs a method call and just returns the task. There's no more overhead in terms of generated code and things that has to run, right? So sometimes the right approach is to not introduce async and await. Sometimes you can just return the task. But it's really important that at the top level, that would be inside, in this case, the main thing or the main method that executes this program, that's where you have the await. That's what awaiting or using async and await all the way means. At the top level or at some level in the application, you have to validate the entire chain of method calls. But unless there's anything inside the continuation, you don't have to do the async and await keywords. So async and await, or async all the way means that you should avoid introducing unnecessary state machines or unnecessary async methods, but you should await at the top level. That could be the main method or in the click event handler, for example. All right. Then I guess the idea of how do I cancel one of these tasks is if I have a long method or a long chain of asynchronous operations, how do I make sure that if I want to be able to cancel this somewhere in the application, how do I do that? Task doesn't really have anything in terms of just knowing exactly how to terminate itself. You can't just tell a task to, hey, I want you to cancel. You can't just pass what's known as a cancellation token and think that it's going to work out of the box. You have to write some manual code to handle that because you don't know in which portion of your asynchronous operation this cancellation would occur. And if you cancel an operation, do you want partial data? Do you want to roll back? Or what do you want to do with that? You have to handle all of those different situations yourself. Let's say I have this method called long-running operation. This is a while true loop that just prints something out to a window here. It writes the ticks to a debug window, and then just has a wait task.delay. If I run this using a task.run, as you'll see here, I'm going to pass something called a cancellation token. The cancellation token source is something that allows me to signal that I want to cancel an asynchronous operation. And I can pass the token into this asynchronous operation, but when I then say that I want to cancel this, nothing is going to happen. Because how would this method know how to handle this? This here is executed on a different thread. If I tell this to cancel, how would it know where to stop? It wouldn't. It wouldn't make sense for this to just automatically know where to cancel itself. So instead, you have to introduce a little bit of code to handle that properly. In this case here, I say that if someone has requested a cancellation, I want to throw an exception, and then I can handle that properly. Maybe I need to roll back this last portion of the code. Maybe I need to send some signal somewhere else or do something. So keep that in mind, because this is something that bites a lot of developers quite frequently, and then handling how to approach that in different situations. what happens if you cancel, or the cancellation happens at the top or at the bottom? Is that going to behave differently? Is that going to change the behavior of how you handle that potential cancellation? All right, so another, in terms of efficiency, asynchronous operations with databases is really important. Like when you want to load data, that's one of the main places where you want to introduce asynchronous programming. It's when you talk to your databases or when you talk to your web APIs. When it comes to Entity Framework, it doesn't support parallel operations on the same context. So for those situations, you should always use the await keyword on each of those different asynchronous operations using Entity Framework. If you try to be smart here and optimize this yourself, you're going to run into situations where it doesn't work as expected. So always await your calls to your database when it comes to asynchronous or when it comes to Entity Framework. So the final thing I want to talk about is how to stream data. If you were at my C# talk yesterday, you saw an example of how to stream data using asynchronous principles. And this is done by introducing something called an Async Enumerable. This allows us to consume a stream of data asynchronously. Let's say that I might be getting something from the disk, or I might be getting something from the web, or maybe I'm listening to an MQTT server, and I'm listening for data to be fed into my application. And I can then use an asynchronous enumerable to do that. Let me show you an example of this. It's harder to exit PowerPoint than it is to work with asynchronous programming. Let's see here. I have an application here. It's a WPF application again. I've introduced a method here called getLyrics. It's an async enumerable of strings. So this will stream strings into my WPF application. What I've also added here is that the capability of canceling this operation whenever I want. And I've decorated this with an attribute called Enumerator Cancellation. This allows me to set the cancellation token in a little bit of a different manner than you might not have, instead of passing it into the method yourself. And I'll show you that when we consume this method. Inside this method, I'm opening a stream to a file on my disk. I'm simply saying that I want to load some lines using asynchronous principles. So notice here that it's marked as async. I use the async enumerable. This is a task-like thing, so it knows exactly what to do when it sees the async keyword together with the async enumerable. I have the await keyword say that I want to load each line asynchronously. And then if there's a cancellation, I'm going to throw an exception. So whoever uses or consumes this stream of data, they can handle that properly. Then I process each line. So it takes about 400 milliseconds before I use yield return to signal that I've now asynchronously processed a line or a result. You can now go ahead and handle that. It's important to know here that we have no idea how many lines there are here. So in terms of writing efficient code and writing code that might not fail, you never want to call toArray on your enumerables or your async enumerables because you don't know how much data there is going to be. Right, so when I consume this, let's have a look at how we do that. Here's a for each loop that has an await in front of it. This looks a bit different from what you might have seen in the past. Normally, when you have an asynchronous method, you have the await keyword in front of the method call to say, run this method, and once there's a result available, I want you to come back to this particular portion of the code. But in this case here, the await keyword is in front of the for each loop, because what we're saying here is that each line that comes out of this method called getLyrics is going to be asynchronously retrieved. So effectively, what happens here is that this here is a continuation. Each time we have some data that's being passed back from that asynchronous operation, we're going to run this code back on the UI thread. That's a big difference as well from using the task parallel library. After the await keyword, all code is always executed on the original thread. That's a really important difference between using the task parallel library and async and await. And then you see here that I have this method called with cancellation. This is what's passed into that the decorated attribute, the enumerator cancellation. Because maybe I don't own this method call. Maybe this async enumerable is a property or it's coming from somewhere else. So I can pass in the cancellation using this method call. All right, so if I run this here, see if it works. Where is my UI? Here we go. Run. Perfect. That worked. Best song in the world. All right, let's push cancel here, and hopefully that worked as well. Cancel. And the operation was canceled as well, so it handled that cancellation properly. So these async enumerables are really powerful to get data streamed into your application, and you can use this in many different interesting and cool situations to make your applications work a lot more efficiently when it comes to a lot of data that needs to be processed. But just keep in mind that you should never ask for it to be converted into an array, because that is going to take a lot of time and processing power. I have a whole course, so if you have 4 hours to spare, I'm going to detail in a lot about asynchronous programming. There's really much to cover when it comes to both parallel programming and asynchronous programming. And if you like that course, I have about 20 more. So if you have like a few weeks to spare, like if you want to learn about game programming in Python or the latest in C#, go ahead and check my Pluralsight courses. And again, I hope you found this really useful. I want to thank you so much for listening to me. If you have any questions about Async and Wait or anything in C#, feel free to reach out. Thank you again for having me here. It's been a pleasure.